so much, everyone, for coming here today. My name is Erica Lestigian, and I'm a principal software engineer at EBSCO Information Services. My primary focus is to design search solutions for EBSCO Health. We are the leading provider of evidence-based content for point-of-care practitioners. Our search engines are one way in which we deliver this content to our end users. For example, a physician in the emergency room may use our search engines to diagnose and treat patients. Now, our end users are extremely busy individuals. A 2017 survey of emergency room physicians showed that 62% of them spend 12 minutes or less with each patient. Now, this is actually a common trend across many specialties. But not only are our end users strapped for time, but they also need to consume a very large volume of medical research that's published annually. So my mission as a search engineer is to deliver the most precise search results as possible. My goal is to shorten the time it takes to answer critical clinical questions. So really, precision is absolutely key. This past year, I had the opportunity to redesign one of our search engines that powers Dynamed. Dynamed is a semantic search engine powered by a very robust medical knowledge graph. Now, this knowledge graph has over 10 data sources coming together to create over 300,000 medical concepts. We use these concepts in two ways. First, as part of our content ingestion pipeline, we enrich content that comes in and store it in our index. And the other use is at runtime. However, just because I have a robust knowledge graph doesn't mean I actually understand the intent of the user. So today I'm going to walk through some examples that illustrate this, and then talk about the ways that we solve this with query intelligence. So let's take a look at this first query. This query for AF is actually quite common. It's extremely ambiguous. You can imagine physicians, they often think and write and speak in acronyms. Now it turns out that AF could mean amniotic fluid or atrial fibrillation. We actually have over 16 concepts in our knowledge graph that map to the term AF. Now, I should mention, at indexing time, I have the ability to disambiguate these acronyms because I have context. But at search runtime, I don't have a way to disambiguate it. So if I were to simply leverage the information coming back from my knowledge graph, I would have far too much recall and not enough precision. So clearly I need a way to do better in this area. We also have very general queries that we see. So breast cancer is an example of this. On the right-hand side here, I've indicated some sample titles in our content where breast cancer is mentioned. Take a look at those titles. Do you see a common pattern? What we have here is breast cancer as a singular concept joined with another one. We have breast cancer screening, breast cancer women, inflammatory breast cancer. Now, when the search engine calculates its relevancy, how is it to know which one is more relevant than the other? Now, I know actually that the target title that I'd like to show at the top is breast cancer in women. But I need some way in order to create that effect. Now, sometimes we don't have any ambiguous queries or very general. We have some specific queries, such as headache. So headache, I can semantically understand. But here's the problem. Headache is a common side effect in many drug content, and it is also a symptom in our condition content. Now, the intent of a doctor when they're inputting symptoms is to diagnose. So really what they want to see is this condition content. But if I, again, just use what comes back from my knowledge graph, I'm going to have way too much drug content showing. Now, I think as everyone in this room is aware, when users input terms into a search box, they don't often take into account the order that the terms are entered. This is a classic example, paralysis facial nerve treatment. Now, a brute force approach of inspecting my graph would yield that I have 4 distinct concepts associated with these terms. But again, I told you that precision is my main goal. So as I continue to inspect my graph, I can see that I've been able to combine facial nerve together into a singular concept. But I know I can do better. So here you can see that by applying permutations, in addition to further analysis with my graph, I can now correlate paralysis facial nerve to a very specific concept in my graph called facial nerve paralysis, which is the same concept that's represented when I index this content. So great, I have a very precise way of interrogating my graph. But here's some problems. Take a look at Zoloft pregnancy. Zoloft is extremely precise, it's a brand. But I don't actually have a lot of content where Zoloft is mentioned. The majority of my content actually refers to the class of drugs, antidepressants. Okay, so I have a very precise concept, but it doesn't mean I can match content in my system. Well, I mentioned I have a knowledge graph. So what I can do is I can inspect my graph and look at the ancestors associated with it. And here we go. I've made this key connection between antidepressant and Zoloft. But look at what happened to pregnancy. I lost quite a bit of precision here. Clearly, this is not the intent of the user, right? No, the intent of the user is that they're really interested in antidepressant or Zoloft and pregnancy. I also have quite a bit of users that search for drugs. Now, this particular use case, the intent of the user is that they want to know how effective Zoloft versus Wellbutrin is. And again, if I inspect my graph and I look at these relationships, I can see that they have a common ancestor. They are both of the class of antidepressant. This is great. But if I go ahead and I extend this same logic to different use cases, it fails. Let's take a look at Humira and rubbing alcohol. When I look at the relationships in my graph, I can find commonality between them. But clearly the intent of the user here isn't to compare how effective Humira and rubbing alcohol is. No. The intent here is that the user wants to understand how to apply rubbing alcohol prior to injecting Humira. I also have drug searches where users are looking to understand an interaction between 2 drugs. Zoloft alcohol is a classic example of this. And again, I can look at my ancestors and try to make some assumptions based upon a lack of relationships or the presence of relationships. Now in this case, I have no common classification for this drug, but that really doesn't mean that I have a high degree of confidence that they're looking for an interaction between these 2. So really what we're trying to get to is this idea of clinical intent. Our practitioners oscillate between different phases of patient care. Sometimes they're focused on prevention, other times they're really focused on the diagnosis, treatment, and monitoring. So really what Query Intelligence aims to do is create a system upon which we have a foundational knowledge and then we can layer more intelligence around it. So imagine it like a snowball. You have a core ice, and then as you remember as a kid rolling a snowball across your lawn, you get these more layering around it. The end output here is that we have recommendations. So let's take a look at what actually is under the hood of Query Intelligence. So Query Intelligence is a microservice with a plug-and-play architecture. What I really wanted here was the ability to fail fast, plug in new ideas, take old ones out. I need incredible visibility. I need my stakeholders to understand what recommendations I'm providing in order to construct my matching and ranking criteria. Now I have two classifications of plugins. On the left-hand side here, these are product agnostic plugins. They're really the kinds of plugins that you would expect that can create basic general information. So let me give an example. When someone searches for girl, I can understand that girl is a female, so I've understood the gender, and I can also understand the population is that of a child, right? So I can essentially reuse these plugins across multiple products. Now on the right-hand side here, these are product-specific plugins. So I had mentioned at the beginning that precision is really important to me. So I have some plugins upon which I have a deep understanding of the structure of my content. So when someone searches for something such as management or treatment, I can leverage that information to take them directly to a section in the content that correlates with their search. So really, when we look at the way that you construct and work with query intelligence as a microservice, as an engineer, is that essentially we have these different workflows and workers, and they can be interchanged. You can think of it many ways as a bunch of Legos on the floor. One day I want to build a tower, and another day perhaps I want to build a wall. But really the goal here is to be flexible, fail fast, and support experimentation. So let's put this all together. The medical search platform receives a request, and what it does is some heavy pre-processing. It goes out to query intelligence and it asks that question: what is the user's intent? Query intelligence comes back with a series of recommendations, and then the platform constructs runtime specific search strategies. So what I'm really trying to get to here is, if you imagine searches that fall under a bell curve, right? I have a majority of searches that can fall under this main use case. And then I have these outlier use cases that I want to solve. And what I don't want to do is have the whack-a-mole problem, where I tune for this and then this goes up and tune for that, right? I want to be able to solve all of my use cases and have them all live in harmony together. So let's go ahead and look at some of the recommendations that come out of this engine. So here's an example payload that comes back from the engine for a query of AF. And if you recall, AF was very ambiguous. So what you first see here is that I have narrowed down those 16 concepts into one. So what I have done is we have an extensive staff of physicians and doctors that consult with us on user intent and really on our graph. And what they have indicated is that, you know what, if you don't have any context, go ahead and assume that the end user is thinking of atrial fibrillation. Now, it so happens that this actually supports my click-through data. So the advice from my subject matter experts is backed up with evidence of click behavior. You can also see here that I've recognized that atrial fibrillation is a category in my content, and so therefore perhaps I should consider also returning results within that area. So let's go ahead and take a look at the results in Dynamed. So what you can see here now is, since I have done a default context disambiguation, that I have far more precision in my results. All of these titles really relate to what my target preferred acronym is. Let's take a look at Zoloft pregnancy. So again, I have a semantic recommendation that has come back from my knowledge graph. And I've identified that I have two primary concepts here: Zoloft and pregnancy. But look what I did here for product under Zoloft. I executed an automatic hypernym expansion. And what you see here are that there's concept IDs associated with that expansion. And these integers, 1, 3, and 2, really represent the distance of that concept to these expansions in the graph. What you will notice here is that I have not expanded pregnancy. Pregnancy was specific enough. I would also like to note that those numbers that are represented up here are essentially used as part of a decay weight at runtime. So I'm able to essentially boost certain pieces of content that are closer to Zoloft versus those that are farther away in the graph. And again, you can see here I have a content type recommendation for drugs. So I've recognized that because the end user searched for a particular drug, that perhaps I should also consider boosting those contents. So let's go ahead and look at the results on Dynamed. So here I have the exact hit that I've been looking for. This is a result of that hypernym expansion. Antidepressant use in pregnancy and lactation. I also have here the result of a content type recommendation. So this again is the drug review. So because I was able to identify that they searched for a drug and boost that drug content, I also got a desired result there. Let's take a look at breast cancer. So as you remember, breast cancer was very general. And here, essentially how I have solved this is by using the click-through recommendation. So as I had indicated, my target title was breast cancer in women. And so now I'm able to leverage that click-through data as a tiebreaker. Again, I have also recognized that there's a particular category associated with breast cancer, and will return that as well. So here's the outcome on Dynamed. You can see exactly what I had hoped for is happening. Breast cancer in women is now what will naturally be floated to the top. And finally, let's take a look at Crohn's children and managing. So what we have here first is that I've recognized that managing corresponds to a structure in my content. I've also recognized Crohn's as a disorder, and then children as a population. So I've essentially taken that query, I've segmented it into different components, and here's the end result. The first hit is really a combination of all three of those recommendations together. You can see that reflected in the title. We have management, Crohn, and children. So naturally, it's going to be boosted to the top. Now, the second hit is also excellent, and you can see that there's a distribution of two recommendations at play here. We have Crohn and children as the title, and then look what we have here. I've taken them directly to that management section that they were interested in. Now, query intelligence is very much in its infancy. We're just essentially at the beginning stages of where I see it in the future. So if you recall, so one area that we want to essentially improve upon is how do we take in geographical locations into account when recommending particular types of content. So you can imagine if there's a hurricane in your area and a physician is trying to treat you for nausea and diarrhea, perhaps they want to get better access to waterborne illness conditions. Additionally, different governing bodies have different guidelines for treatment. So we definitely want to take that into consideration when we go ahead and build our recommendations. Now, earlier I had indicated that I created a default context when I had a lack of one. But clearly I can also do better in this area here. So personalization in terms of what is the specialty of the end user, and perhaps their previous click history. So an obstetrician, perhaps I'm going to default them to amniotic fluid. We are also engaging in more guided discovery. So you could imagine a physician in the emergency room speaking to a chat box as it's performing a surgery. And essentially what we'd like to do here is really be able to engage more with our end users to help us with that process. And then finally, we obviously will want to incorporate more data into these recommendations. I gave you some examples of differences between drug interactions as well as drug comparison. If I have more data, the confidence score associated with those recommendations will be obviously much higher. So thank you so much for your time. I think I just made it for the 20-minute mark. So please, if you have any questions, I would love to hear them.